this computer. Hopefully I have enough space. Yeah, I have enough space. Okay, so I'm gonna ask you to actually prepare a pen and paper and follow the presentation with me. I'm not going to show you any specific slide, but please have your MATLAB open as well. So we basically do a practice together rather than having
MATLAB.
Yes, MATLAB, pen and paper. So these two.
All right, hold on.
Yeah. So it's going to be a tutorial style rather than
That's
a
good.
session.
That's good.
Yeah. Okay. I can turn it. Let me share my screen. Okay, we're going to talk about bond graph. The idea of bond graph is when you have a system with multiple domains, for example, if you have a DC motor that is connected to a gear that pumps a flow for you, and that is connected to a series of valves, and also you have the power supply and a resistor. The idea is between the different domains, oops, what happened? The idea is between the different domains, electrical and mechanical because of the motor, and then fluid. The only thing that remains constant regardless of the type of the states is the flow of power. So the only constant term that is the only unified term between all of these different domains is power. So if we can model a system regarding the flow of power in that system, we are not constrained to a specific domain, and we are not constrained to a set of equations only. So the first concept in bond graph modeling is flow of power. Power in mechanical systems, P is defined as the force multiplied by velocity. Okay. So you may guess that force and velocity will be the states in a bond graph model. Okay, keep that in mind. The second thing is each of these systems, all of these systems have common behavior regardless of the name and the physics. In all of them, we can see that we can see elements that relates the force to displacement. If I remain in the mechanical domain, displacement, I show it by X. And what is that? What is that? The element that relates force to displacement in mechanical systems?
Force, work.
No, a specific physical elements like
spring.
I wanted actually a spring. because there we have force equal to kx. So a spring relates force to x. Florence Leon, you can contribute as well. What is the element there that relates force to velocity?
The damper.
That's a damper, yes. And the element that relates force to acceleration,
The mass.
is a mass. So the second feature of a bond graph is we can reduce any system element, regardless of the nature of that system, through three types of elements. So keep these two in mind. I'm gonna scroll this very good table in the Wikipedia page on bond graph. This lists the velocity, basically force, the displacement, momentum, and damping mass and spring, but equivalent of those in different domains. Okay, as we said, we work with power. Power relates velocity and force, so we call that flow and effort in a bond graph in general. Equivalent to that in a mechanical system, for angular mechanical system, the velocity becomes angular velocity and the force becomes torque. For electromagnetic system, the velocity is current and the torque is, the force is voltage. Okay? Then we know that for the velocity is basically, if we integrate velocity, we get displacement in linear mechanical system. And if we integrate force, we get the linear momentum. Okay? In general term, we call that generalized displacement and generalized momentum for our system. And equivalent to that is, for example, angular displacement and angular momentum for an angular mechanical system, and charge and flux for an electromagnetic system. The same for electromechanical, for hydraulic and pneumatic systems, the velocity becomes flow rate, force becomes pressure, displacement is the volume, and the generalized momentum is fluid momentum. So you see, in different domains, we have different names, but the same concept. Regarding the three elements that we can identify in these systems, for mechanical systems, we talked about damping, mass, and spring. For angular mechanical system, we have angular damping, moment of inertia, and angular springs. And for electromagnetic system, we have resistance, equivalent to damping, inductance, equivalent to mass, and capacitance, equivalent to spring. Okay, or basically inverse of a spring. For hydraulic systems, fluid resistance is equivalent to resistance or damping. Fluid inductance, I'm not very familiar with this, but it's basically the mass per unit volume. It's equivalent to the mass, and we define something called a storage, equivalent to springs. You need to be familiar with the hydraulic systems to understand these terms. For example, a storage it can be a column, a tank of water, and the height of that tank represents the capacitance of that tank. Okay, we won't talk about this, but up to this point, I want to just mention that bond graph works with flow of power. It defines based on the flow and effort, which is equivalent to velocity and force. And secondly, each system can be defined in terms of three elements: a resistance, an and inertance, which let's call it mass, and compliance or springs in terms of mechanical system. Okay, so that's basically the only concepts we need to know. The figure here shows the relation. Effort, if we integrate it, we get the momentum. If we divide it by capacitance, we get the charge or displacement. And if we divide it by resistance, we get the force. So this line is a resistor. The relation between force and Q, charge or displacement, is basically through a capacitor. So we know that the relation between the flow and the charge is through integration. So we know that flow or velocity is integral of charge or displacement. And the relation between the flow and momentum is through the inertia. So we know that the velocity multiplied by the inertia gives us the momentum. Okay, this is generally useful, but the only important thing is understanding flow effort, the relation with displacement and momentum, and the three basic elements. Okay, that's it. Let's jump into solving a system. The session, this is the examples, this is the sessions. Okay. I start with a simple mechanical system, a simple system of mechanical elements. I assume we have a spring, a damper, and a mass. And a force is acting on that. So we can draw the bond graph for this system in two ways. One way is drawing the flow of power. So if I start from here, the power flows through the mass, but then at this location, it just divides into two parallel flows. Okay, on the way, part of it goes through the mass, and here part of it goes to the spring, and part of it goes to the damper. Okay, just pay attention that no energy goes to the wall unless you have a damper or spring behavior for the wall, or you have a sink or source or another force acting on the other direction. So when you draw the diagram of the system, just draw the diagram of flow of force, flow of power in the system. Okay, now let's draw the bond graph. The force is shown by a source of effort. Source of effort is a source that assigns the effort to the system. And here for mechanical system, the effort is F. Then we draw an arrow. That arrow shows the direction of the flow of power. Okay, so basically the direction of the arrow is equivalent to a coordinate system, but for bond graph systems. Okay, then we have part of it going to the mass and part of it flowing forward. Okay, when we reach an element, for example, here we've reached the mass, we need to ask ourselves what remains constant through this element on the both sides of this element. So we know that we are talking about flow and effort, basically velocity and force. So let's ask which one remains constant across the mass. the velocity remains constant or the force remains constant?
Force remains constant.
Exactly. So when the force remains constant, we set a 0. Okay, so basically a 0 joint is a joint that the force remains constant. Okay, then we reach to this junction, and in this junction the power flows in 2 directions. When we reach a junction, we have to ask what is divided or what is collocated at this junction. Okay, so here we see that the force coming out of the mass is kind of flowing 2 directions, right? So what is being basically what is being splitted between at this junction? Is it the force or the flow? Basically,
The flow remains constant.
So the flow remains constant. That's a good thing. But you know, when we reach an element, we ask ourselves what remains constant. But when we reach a junction, we ask what is distributed or what is collocated. Here, the force is distributed, right?
Mm.
Okay. So since the force is being distributed, we use a one junction. A one junction is a junction that collocates or distributes the force. So basically, the force around it doesn't remain constant. Okay, and then we reach our spring. Again, part of the energy goes to the spring, and part of the energy on the other side goes to the damper. Again, in the spring, we ask ourselves what remains constant across the spring. So what is similar on both sides of the spring? Any answer?
Give me a second. What did you ask? I was taking note here.
Okay, so the question was, so let me probably do it like this. So first step is diagram. Second step is draw power flow. Third step is for each element, for elements, ask what remains constant. Across. And fourth step is for junctions, ask what is distributed. Okay, so if I start again, we had the diagram, we draw the flow, we identified that, okay, the flow goes through the mass, part of it goes to the mass, then it flows through the spring, so part of it goes inside the spring and part of it comes out, the same for the damper. But since the wall is basically not a damper or a spring or whatever, it's a dead end, nothing is there, okay? Starting with drawing the bond graph, on this side, this is a force. We show that with source of effort. Then we draw the arrow, and then we have the mass that the part of the power is flowing through. I ask again, what remains, and we did a mistake in the previous draw. What remains constant on both sides of the mass? So what is constant before the mass and after the mass, between the effort, the force, and flow, velocity?
The force.
So F and velocity again. F and velocity. So I actually I agreed with you in the pre just before, but it's not. Actually, before and after the mass, the displacement, the velocity remains the same. So Trish, do you see this? You know, before the mass and after the mass, there is no change in the velocity, right?
Oh, because it's the same element. Yeah.
Yeah, exactly. It's just a rigid body. It's a rigid mass, so the velocity doesn't change. But if you think good, we see that the force is actually changing because the inertia is adding to the force. Okay, so part of the energy flows, but since the velocity remains constant, we use one junction. Okay, so it basically says, we can say one junction velocity, or let me write, flow remains constant. Okay, then we reach the junction.
One junction, right?
Exactly. Why? Because across the mass, the velocity remains constant. Okay, so it's a one junction, flow remains constant, which is velocity here.
But that one, like the mass is actually the element, right? So we haven't passed through the junction that crosses into spring and damper.
Not yet.
So yeah, so do we consider that as a junction also, or?
Not the mass, just after the mass, we have the junction, right?
Okay, so you wrote there at just below the arrow of the mass, one junction.
Yes.
Flow.
Yes.
So you still consider that as a junction.
Exactly. And you know, in drawing the flow diagram, you see, I just since to match it better with the definition of a bond graph, I put mass, spring, and damper just beside it. Okay, because to basically wanted to get you one step closer to the bond graph definition. So every element is a junction. Also, every junction is a junction. So every element in the diagram is a junction. Every junction that you see is a junction in the bond graph as well. Okay, so we basically, I can say that both will be junctions in bond graph. So now that we did it, we are at a junction. So the question is, what is distributed in this junction? So we have power coming out of the mass. Now we have a junction between the force and velocity, between the effort and flow, basically. Let's work with the mechanical terms, force and velocity. What is distributed between these two elements? A lot on these two elements.
Force is distributed.
Exactly, force is distributed. And the junction that distributes the force is a one junction. Again, okay? So basically, flow remains constant.
The velocity is common, right?
Yes, flow or velocity remains constant, common. Force is distributed. So we set a 1 there. Now we are, again, we have an element. We have a part of the energy flowing through the element, part is passing through. Also here, part of the energy is flowing through the damper, part of the energy passes through. So for the spring, what remains constant across the spring? What is similar on both ends of the spring? Is it the velocity or is it the force?
Force.
This is the force, exactly. So we set a 0 here. And the same for a damper. We know that both sides of the dampers may have different velocities, should have different velocities. So again, the force remains constant. So we set that to 0. So basically, here we had force distributed. Here we had velocity remained constant. Here we have force remained constant. And again, here we had force remained constant. Okay, and as I said, there is no place for the remaining of any part of the energy to flow past to the wall, so there's nothing there. Okay, and if I want to take a note, 0 junction, here effort remains constant or common. So comparing the 1 junction and 0 junction, we notice that in 1 junction flow remains constant, so force is distributed. In 0 junction, the effort remains constant. So what is distributed here? The flow is distributed in a 0 junction. Okay, that's how it is. That's how easy it is. And we know now the definition of a 1 junction and a 0 junction. Okay, let's basically try to write the equations for this. Before writing the equation, note that we can do some simplifications. Okay, what can be simplified? Basically, we don't need these lines anymore. It's not going anywhere. This 0 is unnecessary because there is only one element connected to it. So we can kind of directly connect K and B to the 1. And also we have 2 1 junctions repeated after each other without any parallel elements. So we can mix those 1 junctions as well. What we get is, after simplification, we get only a 1 junction and we have a mass, we have a spring, and we have a damper. Okay, you may say why I didn't do it the simplified version sooner, because it's basically getting from diagram to the bond graph is usually tricky. You need to do it once this way and then simplify. Okay, that's one way of driving a bond graph. The other way of driving a bond graph is, so probably I don't talk about the other way. The other way is less effective. It works only for mechanical systems pretty well. So, and we don't have time, so I disregard. Okay, what about deriving the setup equation of, now I have the system. What about deriving the setup equation of the system? Okay. We know that these arrows show the flow of power. So each of them has an effort and a flow. So basically it's E1, F1, and I just name it to use it later. So E3, F3, and E4, F4. So each of these arrows have an effort and a flow associated with it, okay? What about the elements? For source of effort, it basically sets the effort. So it's E equal to a force in this case. For the damper, we know that the effort is equal to the damping multiplied by the velocity, the flow. For a spring, we know that basically the force or flow or effort is equal to K multiplied by, I name it Q here, displacement. Okay, so basically effort is equal to KQ displacement. And for M, we know that it is the effort is equal to M multiplied by time derivative of flow. So it's for M, it is, what happened? Sorry, for M, it is effort equal to MA, which is basically MF dot. So we can basically write, if I integrate from both sides, I end up with the integral of effort is equal to MF, and the integral of effort is basically momentum. So equal to, and momentum we show it by P here, MF. Okay, that's why the momentum, the definition of momentum and the definition of the displacement is important. You see that we have the displacement here and we have the momentum here. Okay, then for the junctions, in a one junction, all of the flows are equal. So Fi is equal to Fj. And the efforts are, the summation of the efforts is equal to 0. For, and this is for one junction. For a zero junction, this time the summation of, efforts are equal, and the summation of flow becomes 0. Okay. So in terms of the equations, pay attention that we have basically on our unknowns are E and F. EI and FI. Our state space, our states are, what do you think our states are? So the states in a linear dynamic system are the terms that you have the derivatives, the derivative of them. So for example, you have to look for something. If the states are X, there should be X dot in the equations. So what do you think are our states, system states in these set of equations? Where we see differentiation with respect to time. It is basically here and here. So our states are Q, displacement, and P, momentum. Okay, and our set of equations are basically the set of equations we get from writing the set of the equations for the elements, arrows, and junctions. Okay, so it's obvious that we have 2 times the number of arrows as the number of unknowns, and we have the number of springs plus number of masses. That's the number of states that we get, because the states appears only with springs and dampers. Sorry, with springs and masses. The dampers, there is no time derivative.
Can you go back to how we got the states? So states are
okay. So we are trying to find a system of linear a linear dynamic system of
right.
form x dot equal to ax plus b plus b.
Yeah.
Okay. So the states are the terms that we have the time derivative for them.
Mm-hmm.
Okay, and have a look at these set of equations. I can probably expand this one to see it better. It's basically it basically says that we have, if I differentiate from both sides, I get E dot oh, I don't need to do that, but basically if I integrate from both sides, I get integrate of E. Oh, sorry, that's the flow. So I have to differentiate. So I get E dot equal to KF.
Mm-hmm.
Okay, disregard that. This is not important. This is not important here. But the only important thing is basically Q dot is equal to F, right?
Yeah.
Yeah. And the only important thing here is that P dot is equal to E.
P dot
is equal to E. As you see, we had integrate of E getting here. So there it becomes, yes, and there it becomes. So in this whole set of equations, we look for the terms that we can find the time derivative for. Those are the system states.
Okay.
So basically, yeah, Q's and P's are the states, and the number of the states becomes the number of springs plus the number of dampers.
Right. And
also the unknowns, we have 2 times the number of arrows for the unknowns, because all of the unknowns are E1 and F1. E's and F's are the unknowns. Okay, and for the equations, I can come up with the relation for the number of equations. But basically, for each element, we have 1 equation, and for each junction, we have the number of arrows in that junction plus 1 equation, because of this set. So this is equal to the number of arrows coming out of a junction, and this is equal to 1 relation.
Constraint.
Yes, or constraints. Exactly. So now we know the relation for these. Let's try to derive the equations for this one. Okay.
Hey, sorry. Just wanted to clarify, when you say number of unknowns equals to 2 times number of arrows, yeah, can you explain a little bit more? Sorry.
Yeah. So when we try to write the system, the equation of motion for the system, you're gonna understand why. Okay.
Okay.
But
right.
Basically, we are talking about the flow of power in the system. So for each of these arrows shows the power in part of the system, right? And the power is defined by the effort and flow, by the force and velocity. So each of these, so basically each of these arrows represent the power in part of the system, and the power is defined by two variables. So to get the distribution of power in the whole system, we have to basically solve for these 2 multiplied by a number of arrows. And we get the distribution of power in the system.
Okay, I got it. Yeah.
Okay.
Yeah. Nice.
Here, we don't consider Q and P as unknowns. We assume they are known. Okay. You may say why. The reason is we are not really interested in Q and P. We are interested in Q dot and P dot for the dynamic system. And Q dot and P dot are basically F and E. So basically Q dot is flow and P dot is effort. Okay, let's write the equation. Let's basically solve this system then. I'm going to use MATLAB. If you have MATLAB, it's good actually to, it will be a good practice as well. Okay, I just defined the symbols that I'm gonna work with. It's gonna be E1, F1, E2, F2, E3, F3, E4, F4. These are the unknowns. Then I have to talk about Q3 and P2. These are the states. And then I have some constant like B, K, M, and F. Okay, I just forgot to say that, okay, we have an equation. We have an equation for the source of effort as well, which is basically says E is equal to F. Okay, I didn't forget that actually. I've already told you that. Okay, so the set of.
Hadi, do you have to put real at the end?
The what?
At the end of each seams.
No, only for seams you don't need that in MATLAB.
No, if you don't put that, you can get weird simplifications.
Oh, I put real. Yes, exactly.
At the end of the yeah.
I thought you were talking about semicolon. Sorry. So the variables are this. Okay. These are the unknowns, basically. Let's say unknowns. The equations are. Let's write it together. The first equation is. Let's start by writing the equations for the elements. Okay. Here we have E equal to F, right? So it's basically E1. I just write it minus F because it assumes that everything becomes 0. Then for M, we have P equal to MF. So it's basically P2 minus M multiplied by F2. Then for K, we have E equal to KQ. E3 minus K multiplied by Q3. Then we have for B, E equal to BF. E4 minus B multiplied by F4. Okay, these are the equations for the elements. Now we have to write the equation for the junctions. Okay, at this junction, this is one junction. We know that the what remains constant there?
Or I'm still typing.
So we dealt with the elements. Now we want to deal with the junction. This is a one junction. What remains constant?
The so here the effort remains constant.
Yes, yes. So F is constant along this junction. So basically, we can get we can write
is constant.
yes. F1 is equal to F2. Also, F1 is equal to F3. Also, F1 is equal to F4. So that's three set of relations here. And then we have one equation that it basically one junction keeps the flow constant and distributed the force or distributed the effort. So we get sigma if E becomes 0. It becomes E1 plus E2 plus E3 plus E4. Okay. There is no other element, there is no other junction. That's the set of equations that we wanted. Okay, that's it. Then we just write solve. I have a set of equations and a set of unknowns. And let me just name it capital P.
Hadi, on the first row of equations, E1 minus, it should be F1.
Yeah, F1, yes. So E1, F1, that's the equation for the source of effort. Okay, I just solve, I just hit, I have to save it somewhere. And so I got PMF EKQ. Oh, it's capital K. It's capital B. So maybe I said CLC clear all as well. Okay, it is solved. Now to get the system of equations. So basically it solves for everything. So I can set S dot E1 and it gives me the answer. Okay. Now the question is which of these equations are important? We are interested in the system dynamics, right? So we only care about the equation for F3 because it's Q3 dot, and we care about only the equation for E2 because it's P2 dot. So basically the only set of equations that I need is F3 and E2. And that's the system equation of motion. So if I write it down, I'm gonna write as E2. So you notice that this is basically P2 and so P2 and F3. Sorry, X is yeah, P2 and Q3. These are the states. So Q dot becomes basically E2 and F3. Okay, and I have it there. E2 and F3 is equal to, this is E2 minus P2 plus B P2 plus K M Q3 divided by M. And this is the relation for F3. It is P2 divided by M. I just, the only thing that I need is just factoring P2 and Q3 to get the linear form. That's the equation of motion for the system. That's the general approach. You may, so now some hints and heads ups. So one thing is we didn't have any zero junction, but we may have. That's one thing. The other thing is we have other elements. For example, this is a source of effort. We may have source of flow, and there basically the flow is equal to a prescribed velocity. A source of flow is, for example, a hydraulic pump that provides a constant flow, or a current source on a power supply. You can set it to constant current. Okay. The other elements are transformers and gyroscopes. Those elements basically scale up the power, scale up one of the elements in the power. They keep the power flow constant, but they amplify the flow at the cost of reducing the effort, or the other way around. Or they basically change the nature of the elements. For example, they transform the flow into effort and the effort into flow in the other elements. Let's have a look at those examples for that. But before that, you may notice that this was actually a 1 degree of freedom system, right? It had only 1 degree of freedom. Why? How we ended up with 2 states then? The answer is bond graph doesn't give you generalized coordinates. So it doesn't give you the minimum possible number of states for the system. So as a result, you may end up with systems of higher orders. As you can see here, to get the Q, which is the only degree of the generalized coordinate of the system, we still need to solve for P as well, the momentum. So it's not necessarily result in the minimal dimensional state space. Okay, but now let me give you an example about piezoelectric material. Okay, and how it can be done via bond graph. Trish, if you have time, I can actually solve a more complex mechanical system.
It is important.
Okay. Okay. So let's do something something more complex.
Like a motor driving something with a gyrator.
A gyrator, yes, sure. Just before that, let me talk about the concept of causality as well. Okay. So causality is identifying the elements that identify the system flow or effort. Okay. For example, a source of effort, what it defines, what it imposes on the system. Is it the effort that is prescribed, assigns, or is it the flow?
No, I didn't get the question. I didn't get the question.
Okay, the question is the concept of causality.
Yeah.
Okay, the concept, you see that we solve the system without mentioning it. Yeah. So the concept of causality identifies which element in the system defines or basically defines the system, the part of the system flow or the part of the system effort.
Okay.
Let me start with an example. The source of effort. In this part of the system that is shown by this arrow, what is defined by the source of effort? Is it the effort or is it the flow?
It's the effort, right?
Exactly, it's the effort. So the source of effort basically forces that part of the system to have a certain effort.
Flow.
Okay, to have a certain effort. Okay, it's basically like the force here. So the force prescribes the effort in this part of the system. Okay, we show that by an arrow on basically a vertical line on the other side of the arrow. So it basically shows that the part of the arrow that doesn't have this vertical sign defines the effort in that part of the system. Okay, so basically the other part of the system defines what? So if one part of the system, one side of the arrow defines the effort, the other side of the arrow defines
the flow.
The flow, exactly. So you can remember it this way as well. The part that has this perpendicular line, the part that has causality sign, we call it causality sign, it defines the arrow flow. Okay, so we know that source of effort defines the effort, so the causality sign goes the other side of the arrow, and a source of flow defines flow, so the causality sign remains on the right side. Okay, remains in the side of the source of flow. Okay, what about the other elements in the system? In general, the elements, basically the element that has an unknown in its equation determines that unknown for that arrow, for that part of the system. For example, a mass, the equation for the mass at the end becomes P equal to mf. We have F, but we don't have E. We have the integral of E here, which is P. So basically the mass assigns the velocity, assigns the flow. So the causality sign is, which side of the arrow should be the causality sign if it defines the flow?
So on the mass side.
Yes, exactly, it's on the mass. What is the other element that we can identify only one of the efforts and flow in the relation? For example, for the damper, we have both effort and flow. But for the spring, we have only the effort, right? The flow is not there. The integral of flow is there. So basically, it integrates from the flow. It doesn't enforce the flow. So it basically enforces the effort. So these elements are called elements with known causalities. Source of effort defines the effort, so causality is on the other side. Source of flow defines the flow, so causality is on the source side. Mass defines the flow because it integrates from the effort, so the causality remains on the mass side. And a spring defines the effort because it integrates from the flow, so the causality goes to the other side. For the damper, it can do both. So that damper is basically a follower of the rest of the system. It may assign the flow in part of the system, or it may assign the effort in part of the system. Okay, but how to define it here? We can get
on the one side, right?
Yes, we can get help from the junctions. In the one, what remains constant across all of these arrows around a one junction?
Flow.
Flow. So basically, the one junction assigns the flow for all of these arrows except one. So for example, the mass assigns the flow here. So it basically assigns the flow for the one junction. So we cannot have any other elements assigning the flow here. So it becomes like this. If we had a zero junction, the effort remains constant across all of the ports. So the causality is always on the other side of the arrows, except for one. So that basically zero junction defines the effort for all of the ports except one, and that one is the one that defines the junction effort itself. Okay, I'm going to scroll the Wikipedia page, you see all of the variations. But that's the meaning. What is the importance of that? So, okay, I know that this damper defines the effort, but it basically constrained to the flow defined by the system to it. Or the mass defines the flow, but it is constrained to the effort defined by the system for it. The thing is, if you put the causalities and you end up with a junction that it is not satisfied, so for example, you end up with a one junction with two of causalities on the other side. That system is infeasible. So basically, bond graph shows you if a system is not feasible. And those systems are usually singular. And if you define a system that causality is not satisfied, you end up with a singular system. The inverse, for example, in terms of control design, the inverse is diverging. So the causality is, in hydraulic systems, that's important because that causes a lot of vibrations, for example. So the causality helps understanding if a system is physically feasible or not. If the system is fully defined or if it becomes singular at one point. That's the point of it. But and you need to define actually, and the other work, the other benefit of causality is you see that actually getting the bond graph is not that easy from the diagram. Putting the causalities, if you found the causalities are not satisfied, you may find a mistake in your model. So that's another benefit. It kind of tells you if you've done the model correctly. Okay, let me go for a more complex system. Our system of a DC motor that is connected to a shaft with a gear on it, and that gear is basically changes the ratio, and that ratio is basically connects to a constant volume pump, and that pump is passing through a few valves with a certain resistance. And then just draw the water out, something like that. Okay. So if I want to write the equation for this system, I probably do it like this. So I don't close the circuit, so it looks more similar to what we're going to discuss in terms of the elements. So I'm going to have the flow is coming here, then I have a resistor here, then it goes here, again, I have the DC motors. You may know that it has an inductance and it has a resistance because of the back EMF current. And then part of it goes through the mechanical system. Here we know that we have inertia of the gears, but then, but pay attention that here we have something that transforms the electrical power to mechanical power. Then we have the energy flowing to the gear. Again, here we have a transformer because we know the velocity of one gear is different from the velocity of the other one. And also we have inertia there. Then the flow goes to the hydraulic domain. So we have a transformer or a gyroscope there. We have to decide it. Here, so let's assume there is no behavior other than just this transformer behavior for the pump. But then we have a junction here and we have part of the power flowing through the resistors, and then they join together and they go just outside. Okay, and we know outside has a constant pressure of P0. So we have electrical domain, mechanical domain, and hydraulic domain. Okay. Let's start with the system. We have the voltage. Voltage is it effort or is it fellow voltage?
It is an effort, right?
Exactly, it's an effort. The energy goes, and part of it goes to a part of it goes to a resistor. So what remains constant across this resistor?
Flow.
The flow remains constant. So I have to have a one junction there. Okay. Then we end up with part of it flowing through an inductance, part of it flowing through a resistor, and part of it going to the next system. Okay. It really depends on how we assume this inductance and resistance are, but assuming they are in series, what remains constant across each of these?
The current flow. Yeah.
Well, basically the inductance changes the current, right?
But it changes the overall current, right?
The inductance
Whatever
is like...
passes through inductance will go to resistor.
Yes, yes. So basically the, let's say...
The flow is constant,
yeah. So yes, it's like a mass. So the flow is constant. And again, across the resistor, the flow is constant, right? Okay. Then we have here an element that gives us the energy that passes to the mechanical domain. Okay. We know that the velocity of the motor, the velocity of a DC motor, is basically related to the current of the motor, right? So in a DC motor, if you put, so let me do this. So current is proportional to the sorry, the current is proportional to the torque, right? Yes, but you know, the DC motor, higher the torque, the higher the current it takes, right? So now the question is, so what is current on the electrical side? Is it flow or effort?
Flow.
That's flow. And what is torque on the mechanical side? Is it flow or effort?
Effort.
That's effort. So we need to use a gyroscope, because here flow is converted to effort. Okay? The relation for a gyroscope is basically EI is equal to M, the modulation Fj, and Fi is equal to 1 over M Ej. The reason we have M and 1 over M is the power should remain constant on both sides. So anyway, so we use P for the momentum, I know, but power I should be equal to power J. So the modulation is M and 1 over N. Okay, on the mechanical side, part of the effort goes to the inertia. Okay, inertia is like a mass. So the mass, we know that the displacement remains constant on both sides. Okay, then the flow of energy goes from the gear 1 to gear 2. So here is basically I'm gonna identify it later, but this is this part is DC motor, this part is gear 1. Okay. So we know the velocity of gear 1 and the velocity of gear 2 are related, right? Velocity of 1 is equal to modulation multiplied by velocity of 2. So here we need to use a transformer, because the flows, the flow on one side is equal modulated to the flow to the other side. So again, power remains constant. Flow I is equal to M flow J, and EI is equal to 1 divided by EJ. We use simply a transformer. Then again, part of the energy flows to the inertia of the second shaft, and then it flows through the hydraulic system. Again, the displacement remains constant on both sides of a mass, so we have a one junction. The part of the power that flows through the hydraulic system, we have basically the velocity of the motor transforming to the volume, the flow rate of the hydraulic system. Okay, so what should I use? I know the velocity of the gearbox, the gear 2, relates to the flow rate of the pump. The velocity is flow. The flow rate is flow. So the flow is it becomes modulated to flow. What should I use?
It's zero. Sorry.
Is it a transformer or gyroscope? Because we have modulation, we need to use a transformer or a gyroscope.
The transformer.
Exactly, you need to use a transformer. Basically, gear velocity is related to pump flow rate. Then we have a junction that breaks the that distributes the flow, of course. So I need to have a 0 because the flow is distributed across. And then I have 3 resistors. Maybe it's a bit. This is maybe better. Okay, and again, after the power flowing through the resistors, they just come back together. Okay, first we have to decide about this junction. What remains constant across the resistor?
It's the flow.
It's the flow. Yeah, the pressure drops, but the flow remains constant. So we have 1 in all of these locations. And at the end, what is collocated at the end? Is it the flow that is collocated, added up, or is the effort, the pressure?
Pressure.
No, we have basically three currents coming together. It is the flow that is adding up, right?
Yeah, flow is adding.
Its flow is that as in adding up. So we have a 0 there to basically add the flow. And at the end, we have the element with constant pressure. So the pressure, is it effort or flow in a hydraulic system? The pressure is the effort, right? And it is basically a constant pressure thing. So we have to put a source of what type? A source of effort, right?
Yeah.
Yeah. And that becomes our system. We can definitely simplify it. For example, we have 2 ones here. We can.
Hadi, can you go back to the gyrator? So
yes,
in the gyrator, so Fi is the current, right? Current determines the torque.
Yes, on Fi is current, Ej is the torque. Yes.
And then Ei is the?
Ei is the voltage on the electrical side, and Fj is the angular velocity.
Right. Voltage proportional to angular velocity. Yeah.
Velocity, yes. That's how DC motors work. So you hold them. They basically get more current if you keep the voltage constant. Yeah. And the voltage basically controls the velocity of the DC motor.
Yeah.
Not the. So basically, when you get to either the modulation, like the gears that we had here, so from one gear to the other gear, we notice that the flow is modulated, or the transition between usually in between different domains. We need to use gyroscopes and transformers, but you know that, for example, for the transition from mechanical to hydraulic system, we used a transformer, but for the electrical to mechanical system, in this case, we needed a gyroscope. Okay. Let's look at the causality. Let's look at the causality and see if it works. We can start with one end of the system. The source of effort, it determines the effort. So causality goes to the other end. The resistance, it's not determined, it doesn't help. And so basically we cannot proceed any further from this point. And the one junction, we know that, okay, it defines the flow of all of the ports except one. but this port that we have the causality for, it's not defining the flow here, so we cannot again proceed at all. Okay, either we can start from the other end or start from an element with known causality. The inductance, it's like a mass. It integrates the effort, so it defines the flow. So the causality is on this side. Now we can work with the one junction, because now that one of the ports are the flow on one of the ports are one of the 4 ports is defined. We know that all of the other ports flow will be defined by the junction. Okay, and now we can get back to this one junction, because this port, the flow is defined, so the flow of this resistance should be defined as well. Okay, now getting to gyroscope. Gyroscope, basically we define here, you see that this one junction defines the flow of this port. So we basically know Fi. So what, as a result, what is defined on the other side from this second equation?
Flow is defined, right?
On the left side, flow is defined. So on the right side, effort will be defined. It's a gyroscope. Okay. So now if the effort is defined on the other side, where should be the causality? Here or here?
Gyrator side.
No, other side, because gyroscope defines the efforts, right? So ports, the left port, the flow is defined. F is defined. Yeah. So it's a gyroscope, so we use this equation, the effort on the other side is defined. And since the effort is defined, so the causality sign should be on the far end. So that's how basically the causality of gyroscope looks like. The causality sign will be either both inside or both outside. Okay, that's it. Then for the one junction, we don't have the flow determined yet, but the I helps us. It defines the flow of this arrow. Now the flow in the one junction is defined, so it defines the flow of the transformer. The flow is determined here, so Fi is determined. So from the above equation, it determines the flow of on the other side. So the causality sign is on the same side of TR. So you see for transformer, the causality sign is basically one on one end, the other one on the other end, something like that. But for the gyroscope, the causality signs are both either inward or outward of the arrows. That's how the causality sign of transformer and gyroscope should look like. Okay, now the flow is defined for a one junction, so it basically defines the flow for the other junctions, right? So now that the transformer defines the flow of this port, the one junction should define the flow of the other ports. But you see that it's not possible, right? Because the inertia of the inertia should define the flow. You cannot define the. That's actually where you see that the causality is not satisfied. So it says your model has something. Your model lacks something, and that thing can be a resistance in the system, or maybe the model is wrong. But if you have a physical system of this form and you model it this way, you end up with a singular system. But if I don't do bond graph, I won't notice that, right? I just proceed with the modeling, and I end up with a bad behaving system or a bad behaving controller. So we have to actually fix it somehow.
So this feedback loop is not there, right? So the speed defines a back EMF on the DC motor. So there's a voltage induced by the speed. So I think it is, I thought it's coming on the gyroscope. But after the transformer, so you have
yes, it's coming back from the gyroscope here. So this resistance is back EMF basically. Or you're right, I can have another gyroscope to just get back here, but let's not make it more complicated.
So
but here,
the transformer, there's the friction. We can put the friction in the gear, right?
yeah, that may help. That may help. Let's see how to do that. But the friction, for example,
like Coulomb friction.
Yeah, exactly, the Coulomb friction. So assume the friction is on the shaft. Okay. So basically we have a resistor here. Okay. Now the question is what remains constant across the friction, the resistance?
So that is the flow.
The flow, exactly. The flow remains. So I basically need to use this, add it to the same one here. Yes?
Yeah.
But it doesn't actually help because anyway, it doesn't change the causality on this side. But maybe we can assume so if I say the causality is here, it defines the flow here, it is here, and then we have to do something with this. So maybe we can have a 0 here, and we have a resistor here. And it basically says the flow is defined there. So the resistor defines the effort, and it is solved. So this basically this is basically pretty interesting. It says that for the system to well behave, I need to assume a parallel damper on gear 1.
Parallel damper
on gear 1, because see, after gear 1, the displacement remained constant across the inertia.
Right.
But then we need a 0. It says the force remains constant across R and TR. Sorry, it's a series damper.
Yeah.
Yeah, it's a series damper. So it basically the force, and it basically tells you put a resistor in your model and your model behaves better, and even a small value helps. So let's proceed. Again, we have a transformer here. The flow is defined on one end, the flow is defined so on the other end. We have 0 here. The flow is defined here. We need to know which port has the effort defined. So we stop here. It doesn't help. The resistor, they don't help us with causality, so we start from the other. Effort is defined here. So it's basically, that's a zero junction. So you see that effort is, since one port is the effort on one port is known, the effort on other ports are known now. And it's up to us, to be honest, at the moment. So we can say that this resistor, this resistor defines the flow. So as a result, we get, basically we can say one of the resistors.
The end, how did it become a source of effort? Is it a source of flow, isn't it?
No, that's because, this is constant pressure. So it's an open, yeah. It's exactly, it's an open end tube that just pours out the water.
Right. Okay.
Yeah, the pressure is constant here. Okay, and look, Trish, if I assign all of the so I ended up here, and I assigned the causality of all of the resistors so they define the flow. Okay. So I end up with the causality of I end up with a zero port, but none of the ports, a zero junction, but none of the ports, but the effort on the effort for none of the ports is defined. Okay, so basically I have to change the causality of one of them. So basically I change the causality of the top one here. These two remain the same, but since it's a one junction, this becomes the behavior. So here, I was actually, I could set the causality of each of these resistors as I intend to fix the causality of the system. It doesn't matter, I assume which, and it says basically two of these resistors determine the flow, but one of them determines the effort. And now the system is fixed. It is really, so that's it. And then we need to write this set of equations like this. It helps really when you want to do a system of multi-physics, like, for example, here it's a piezoelectric material. We have mechanical domain. So here is the mechanical domain. It's like a spring damper. Then we have a transformer to the material domain. The material domain has hysteresis. We can model it as a capacitor. And then we have the electrical domain, which is just an RC circuit, simple. But again, in this arrangement, you may end up assuming that, and I have a source of effort, so it's a piezoelectric material I'm moving around. You may notice that I need a resistor here as well to model the material domain. The bond graph approach really helps in getting a working model of a system and identifying the necessary elements in the system. That's it. I had the model of that piezoelectric material here, but we don't have time for that. Just to wrap up, following the Wikipedia page, you see the relations for the flow, effort, displacement, and momentum. It talks about the components completely, and transformers, gyroscopes, the junctions, and then determining the causalities, deriving the set of equations, and some examples here. And here is basically deriving the state equation. As we basically practiced all of it. Yep. It was long, but I tried to make it actually hands-on, like you help, we code together, something like that. I hope it was better than just having the slides appearing and disappearing.
It's very good.
Yep, that's it. I send these slides
So
over.
can you send the code for the other, this one?
Yes, I send the code for those two as well. The namings are not complete, but I send the code. And I said the slide as well.
Perfect. Thank you very much. So you recorded it, right? Yeah, let's put it in a box for